So the first thing we now know is that we're in a full-blown climate emergency, that fossil fuels and CO2 emissions is the issue of the day, and that timing is everything. Let's talk about timing really quickly. We've all heard people talking about carbon budgets, but not that many people really understand what that means. So I will give you a very, very short tutorial. And we hear people talking about, well, we're going to meet the 1.5 degrees C carbon budget. The 1.5 degrees C carbon budget, this is the amount of CO2 emissions that we can emit in order to have a good probability, a 67% chance of meeting that 1.5. It's 340 gigatons of CO2 a year. Okay, so what does that mean? Well, roughly we emit about 40 gigatons of CO2 a year. If we peak emissions this year, and it looks like we will peak this year because of the pandemic and probably for a few years to come, but then we're expected to go up again. So we need to be diligent and vigilant. But if we peak CO2 emissions this year, and then we phase out all CO2 emissions by the year 2050, if everybody talking about 2050, well, we're going to do this by 2050, 80 by 50, net zero by 2050. It doesn't work anymore. That gets us 600 gigatons of CO2 emitted, and that's less than a 50% chance of staying under, of meeting the 1.5 degrees C threshold. And that's because we've kept emitting since the IPCC, since the Paris Agreement in 2015, and we've used up a bunch of our carbon budget. So to meet the 340 gigatons, we need a 65% CO2 reduction over the next 10 years by 2030, and then phase out all CO2 emissions by the year 2040 in order to meet the 1.5. So anyone who's saying, well, we're going to do this by 2050, that doesn't wash anymore. And why is that so important? Because once you go past the 2 degrees C, the planet keeps on heating. There's so much inertia and CO2 in the atmosphere that conditions get worse and worse and worse, and climate change essentially in any time in the foreseeable future becomes irreversible. The only way we can get a handle on climate change and temperature rise is to meet that 1.5 and then begin drawdown. And there's natural drawdown. The planetary temperatures then begin to come back to the temperatures we've always known. It'll take a while, but that's the case we want to follow. Okay, so between now and 2060, it's estimated that 1.5 million people are going to be added to in and around cities worldwide. We think this will hold even after the pandemic because the wealthy countries are going to put a lot of money into infrastructure, and so we're going to see that happen. And why do we still see cities as growing? We've all heard about, well, the pandemic and cities are really, because of density is a problem. It really is not a risk factor. A study of 913 counties in the US indicates that COVID-19 is not an infection risk factor. It's overcrowding. Not density. It's when too many people gather in one specific place. And what we're finding now is that suburban and rural areas have a much higher death rate than urban cores because there's less access to healthcare and medical facilities. So density is not a risk factor. You can also see that if you look at New York City, for example, and compare that to Seoul, Korea, which is much denser. And has a larger population and has 0.1% the death rate of a New York City. So density is not really a factor. It's how we handle the pandemic. So how do we get to a carbon positive? How do we phase out by 2040, get to a carbon positive environment at that time? Well, it's a two-step process. Step one is what we call planning, design, and construction, and going to electrification. We are going to have to electrify. And then the second step is adding the renewables to meet the electricity demand. So planning, design, and construction, and electrification. That gets us 70 to 80% of the way toward a carbon positive built environment. We call that the no cost, low cost option. And that's everything from urban growth boundaries, public transit, walkable communities, and bringing agriculture into urban areas in glass and glazed structures. That's beginning to happen. So we don't take up all sorts of valuable land and degrade our forests. That's beginning to happen actually on a massive scale. For example, in China, a whole district now is going to indoor urban agriculture. It's also everything from passive heating and cooling systems and daylighting systems where we let sunlight into the building and then store it for use at night. It's a no cost option. Essentially, it's a cost savings option. And daylighting, you all know about all of this and the properties of glazing in achieving this. But we're also now concerned with building construction and building products. We'll talk about that in a bit. We have to get that to zero carbon, and we have to move to carbon sequestering materials also. That gets us 70 to 80% of the way there. Step two is adding the renewables. Obviously, if we're using electricity, and that's everything from on-site to importing and off-site renewables. Just to illustrate that we can get to that 80% is a no-brainer. In the 1980s, this was a library we did in North Carolina, all daylit, 100% daylit library, passively heated and cooled with south-facing monitors, for example. We were able to reduce energy consumption in that building by over 80%. We've done it in housing, for example. We've done it in an all glass, 100% glass building on all four sides. This was a conservatory. It uses no energy for heating, cooling, and daylighting, except for lighting in the evening. Zero energy. So how did we, in an all glass building, use no heating and cooling in a Mediterranean and a desert environment in Albuquerque, which is neither of those environments? Well, we used this was a fairly crude back then. This was the 80s simulation model. This is Albuquerque temperature. And we see it gets pretty cold in the winter and very hot in the summer. This is a Mediterranean environment. So for example, LA is a Mediterranean environment. There are other Mediterranean environments, but this is roughly the temperature profile of a Mediterranean environment. What we did is within the model, we kept altering the properties of the glass on different sides of the building where we needed more transmission, more solar transmission, a better U value. So the glass on each side of the building is different, although it looks all the same. And we were able to then bring the temperature profile within the Mediterranean pavilion. This is actually monitored data over a year to match that of a Mediterranean environment without any energy input at all. If we look at what's happened since 2005 to today, we see that this is gross domestic product. We had a little bit of a recession in 2008, 2009, but then GDP took off and we had a very robust economy. And when we have a good economy, obviously we build, and building floor area went up 47 billion square feet during that period. But look at what's happened to energy consumption in the entire building sector in the US. Even though we built 47 billion square feet, energy use is down in the building sector 1.7%. And if we look at emissions is down 21%. This decoupling of emissions and GDP and economic activity is unprecedented. In fact, we've saved people by not increasing our energy consumption huge amounts of money. So all of that talk way back, well, if we try to get a handle on emissions, it's going to ruin the economy and everything, is all nonsense. It's actually a benefit. And we're beginning to see that decoupling worldwide, where GDP is going up and emissions is beginning to flatten out. So can we reset to meet the 1.5 degrees C carbon emissions budget? Well, there are three areas we have to address. We have to address new building operations, and all of you are familiar with that. We have to address existing building operations. There are hundreds of millions of buildings out there in the world today, and we have to address those. And then we have to address materials construction and the infrastructure that connects all these buildings up, roads and sidewalks, plants and waste and water. So we have to address all of that. So let's start with new buildings first. What do we have to do with new buildings? Well, we have to bring new buildings in, all new buildings, at zero carbon building operations. So this is building operations. We actually now have the codes to do it. We have zero codes. We actually have an IECC code. With any year IECC that you're using, you can add an appendix onto that. It's in the 2021 IECC code that's coming out this month, and get to zero carbon. So what is a zero carbon or a zero code? Well, it uses the existing code standard. So this is nothing new. You use ASHRAE 90.1 2016 as a minimum. You can, if you're using 2019, you can upgrade to 2019. You can use the 2021 IECC, the 2018, the 2015, doesn't matter. You add the appendix to it. You design an energy efficient building. You use passive heating, daylighting, all of those things. You get a fairly efficient building. If you use the code, you get a very efficient building, the latest code standards. And then you address the remaining building's needs with on-site and, or if you can't do it all on-site, you do it with off-site. It's in the IECC now. So if you're on the IECC system, any city or jurisdiction now can adopt the zero code. China now has developed a zero code, nearly net zero energy plus on-site and off-site. They just need to begin to get cities to begin to adopt it. We're going to talk to them in a few weeks about doing that. And then Europe, at the end of this year, beginning of next year, all European countries are expected to have a zero code in place for all new buildings. So this is happening, and the tools are there and the codes are there. So what about building operations, existing buildings? This is looking at Seattle, Washington from the air. You see those big buildings over there? Those are roughly over 20,000 square feet. And in Seattle, buildings over 20,000 square feet represent only 2.8% of all the buildings. So only 5,000 buildings out of 181,000 are over 20,000 square feet. And they're roughly in the urban core right there. So a very small number of buildings. That small number of buildings is responsible for 45% of Seattle's total greenhouse gas emissions. Let's look at New York. You see Midtown, you see the tall buildings there, downtown, you see downtown Brooklyn, for example. That's where most of the buildings over 50,000 square feet are. They represent less than 2% of the 1 million buildings in New York. So that's 26,000 buildings, a very small number of buildings. If you're looking at New York City as a whole, that small number of buildings are responsible for 48% of total building sector emissions. You can begin to see where I'm going with this. This is Minneapolis. Buildings over 50,000 square feet, that's only 1.1% of the buildings. They're all right there. You can see them right there. The rest, miles and miles of one-story buildings. They're responsible for 47% of emissions. You can see the same thing in Chicago. You can see the same thing in Long Beach along the waterfront. The same thing in Philadelphia, same building topology. A small number of large buildings responsible for 50% of emissions, and then miles and miles of small buildings responsible for the other 50%. So how do you then get to government policies for these existing buildings? Well, you first establish a threshold. What's the square footage where you have very big buildings responsible for about 50% of building sector emissions? Start with your biggest buildings, move down. you'll get roughly a square footage over 20,000 in smaller cities, roughly over 40, 50,000 in larger cities. You'll then have half of the pie. That's 50%. Big building emitters, 50% of total emissions. And then the other half is thousands and thousands of buildings responsible for the other 50%. So now we know where our emissions are coming from, which big buildings, which small buildings. So now we can establish a big buildings emitters policy, and that is a date certain. We say by 2030, you have to electrify those buildings and use renewables for the electricity. And you can do it any way you want, on-site, off-site renewables, efficiency. You have 10 years to do it. You'll usually hit a capital improvement cycle, and if you do it then, the cost is really minimal to do this. That's why you give them 10 years. So you're not forcing anybody to do it in year one, and then provide all sorts of incentives to get people to go first. Give them low interest loans, tax abatements, on-bill financing, equipment discounts, you name it. There are all sorts of incentives you can get. You can get that by 2030, you can get those few buildings to zero carbon and reduce your emissions in the building sector by 50% by 2030. Now, then you have to establish what about policy for all those other millions of buildings that are the other half of the pie, 50%. Well, for all other buildings, we say you require electrification and renewables at building intervention points, when a building is going to usually be renovated or people have the money to do it. So if you're going in for a zoning and use change and the city's giving you something for nothing, well, require electrification and renewables. What about point of sale? Somebody buying a building in any of these cities that have money, the financing's in place, they're usually going to renovate. You require them, again, to go to zero carbon. And you provide the incentives for others who want to do it now just to save money, to go to electrification and then add the renewables either on-site and off-site. That's how you get to the other 50% by 2040. You renovate and get to electrification and renewables by 2040 for the entire building sector in cities that way. And there's a bonus. These policies will not only reduce building sector operations by 65%, but if you renovate a building, so for example, let's say you put a whole new skin on the building, a glass skin, for example, and you use selective coatings and you use vertical solar and things like that. A newly renovated building will not be demolished anytime soon because you put in a lot of money. That saves a huge amount of embodied carbon, and we'll talk about that, the core and shell of a building. So you get a benefit, big benefit. Now, talking about solar, we're seeing battery prices tumble and threatening gas and coal. Solar is now the International Energy Agency. Solar is now the cheapest form of electricity in history. And we're beginning to see solar smash records, even when we have an environment that is not a government that is not conducive to pursuing solar and providing incentives and all sorts of things. In 2016, we had our largest increase in solar in gigawatts. We had 17 gigawatts. This year, we installed 37 gigawatts of wind and solar in the US. Think about that, 37 gigawatts. If we do 40 gigawatts a year, we phase out carbon within the time frame to meet the 1.5, 40 to 45 gigawatts roughly. Because every time you add a gigawatt, because energy consumption is not going up in the US in the building sector, and that uses almost 70-75% of all the electricity produced. Every time you put in a collector or add a solar collector or a wind farm, you are replacing fossil fuel energy. Just to illustrate this, this is Seattle, Minneapolis, Honolulu, Atlanta. This is the roof and the south facade. This is how much energy free This is energy per square foot of roof area that falls on a roof area free. It's distributed. You don't have to dig up anything. You don't have to do anything. It is there on a daily basis. KBTU is a square foot a year. This is how much energy falls on the south facade, okay, in a square foot over the year. Now, let's look at average energy consumption. This is how much, this is how much energy average a residential building uses a square foot of floor area. Same thing, square foot to square foot a year. BTU is a square foot a year, and that's how much commercial institution. And if you build them to the latest code standards, they use half of that amount or less. So let's look at Minneapolis. That's how much falls on the roof and the south facade. That's how much energy falls on the east and west facade. That's how much a residence, a typical, that's not even built, well, that's built to code in the brighter red. If it's built to code, that's how much you need. You get so much more than you need. Just got to convert a portion of it. Now, we can send spacecraft throughout the solar system and take measurements of the rings of Saturn, for example, and we can't solve this problem. This is energy distributed free to every site in the US, every site. And all of a sudden now people are understanding this, and we have companies like Solar Skyrise, that's a startup company. They will actually, in a city in dense urban areas, estimate your energy consumption, show how much vertical solar you can get, estimate the cost, the payback, and your asset increase by going to solar. So we can do it in existing buildings, in new buildings. It's a no-brainer. And you'll hear, I'm sure you're going to hear about this today from the folks at NREL, is that on the horizon, transparent solar panels are coming, so that every glass installation can actually be an energy generator. You begin to couple that with on-site renewables or plug into the grid for backup, and we should be able to get every building essentially to zero carbon building operations. Okay, now let's talk about the elephant in the room. Those two are actually easy to do, new buildings and existing buildings. What about materials, construction, and infrastructure? Well, there are literally millions of construction materials to choose from. We can choose everything from brick, glass, wood, concrete, steel, vinyl, sheetrock, you name it. There are carpet, paints, wiring, electric bulbs, mechanical systems, plumbing systems. There are so many materials that go into a building. How do we get a handle on all this? Well, this is the way we usually see the pie shape for CO2 emissions. Building operations, we know is 28%. We know we can get a handle on that, new buildings and existing buildings. But industry, everything in the building sector falls under that 43%, plus everything else. The spoons and forks that we make, you name it, furniture. But infrastructure, building structure, substructure, everything falls into that. Well, this 2 years ago, we had a breakthrough. 11% is core and shell of a building. That's the cement, steel, brick, glass, everything else is about 11% of total emissions. But all the rest of the building sector and infrastructure falls into industry, and that's another 32%. So there's still thousands of materials. How do we get a handle on this? Well, we took another stab at this, and we reshaped the pie. And lo and behold, we see that just two materials, concrete and steel, and if you throw aluminum in, which is about 1.5%, but concrete and steel are half of all industrial emissions and over 20% of global emissions, just two materials. Now we see, well, it's kind of like the big buildings, small buildings, concrete and steel and everything else, all the other thousands and thousands and thousands of materials. That's how we get a handle on it. We know that for buildings, the core and shell and that the core, for example, the structure and substructure, that's the concrete and steel, getting that built is about 55% of all the embodied carbon emissions in a building. And then the other 33% is the building enclosure, is the brick, is the glass, is the interiors, is everything else. Represents about 33%. So that's roughly most of the energy and embodied carbon that goes into a building. So the first thing we want to do is get a handle on that 55%, and then all the other materials, get a handle on that. So the first thing we need to understand is that the conversation is changing. This began roughly 2 years ago. And all of a sudden now that we know that concrete and steel, the mainstream media has picked that up, and you're beginning to see a huge amount of pressure put on those two industries. Concrete, the most destructive material on earth, steel makers in the crosshairs, mass timber giving them a run for their money. The concrete people want to talk about mass timber. Maybe it's not that good. But architects now are looking at mass timber as a way to sequester carbon if it's done sustainably and from a sustainably managed forest. It's all northern woods, so you're not deforesting in the global south, or in tropical forests. So it's giving wood and it's giving steel and concrete a run for their money now. That's pushing concrete and steel to change very, very quickly, and they are changing. We'll talk about that in a minute. But as we get concrete and steel under control, the other 33%, the shell of the building, interiors of the building, they're starting to, with just this year now, beginning to see the architecture and design and planning and construction and materials community look at that. So glass, vinyl, drywall, beginning to get a look, and those industries will be pushed to get to zero carbon. So the way we address zero carbon in embodied carbon is to promote low to zero carbon materials. We know glass does a great job with operations, building operations and daylighting and health and all sorts of things. But to get to zero, and we're not talking about net zero now, we're talking about zero carbon. We're calling for a 40% reduction by 2021 in all buildings. We're talking about that starting right away, comparing different companies that produce materials. And then concrete and steel by 2030, and all materials by 2040. So 20 years for all materials. We're beginning to see concrete and steel transform, carbon sequestering in concrete, making aggregate out of CO2, using sustainable wood and bamboo in buildings, biomaterials for insulation, and actually using landscape and soil and urban agriculture for drawdown. So that's all happening. And in the glass industry, we're now seeing talk about increasing the recycled glass content, product optimization, energy efficiency improvements, and electrifying where possible. But that technology needs to advance. And we've seen some talk about hydrogen. So we're beginning to see movement in many of the other industries, because we know we have to decarbonize by 2040. So Architecture 2030 has put out some targets and standards for meeting the 1.5. That means we need a 40% reduction now through efficiency measures. There's all sorts of measures, transportation, you name it, to get a 40% reduction if we can in all materials. Get a 65% reduction by 2030 in 10 years, and then to get to zero carbon building products and construction products by 2040. And we're calling for high ambition companies to try to get a 50% reduction now, and zero emissions in steel and concrete by 2030. And we're beginning to see that, by the way. Electric arc furnaces, for example, for steel. If you just use an electric arc furnace and specify US steel, you get roughly a 50% reduction than a coal furnace, coal blast furnace. And a lot of that material comes out of that steel comes from abroad. This gets us local jobs, things like that. So we're beginning to see all sorts of movement now on embodied carbon, and there are all sorts of tools out there that have been developed in just the last few years to look at embodied carbon in materials. So to finish up, can we meet the 1.5 degrees C carbon budget? This was Toronto back in 1891. All masonry buildings, very thin vertical glass, all single glass, obviously, but mostly masonry buildings, small spans. Spans were from wall to wall. Everything was compression. Look what happened from that time to 2010. The little building, corner building, still stands, the Flatiron building. But look at all the other buildings, all glass structures, high-rise glass structures. So how did that happen? And we can see the same thing, Minneapolis, London, Hong Kong, same building type everywhere. All the glass skyscrapers in downtown areas. Okay, how did that all happen? Well, it started in 1925 in the Bauhaus. Structure moved in. We started getting concrete structures, post and beam, and that meant we can hang the wall off of the structure. And essentially, this was roughly the first curtain wall building, which was all glass. We put the heating units by the glass and tempered. Energy was cheap, so you could have single glass buildings. That was 1925, was the first modern building. This was going on in 1925, was the Model T truck. It's pretty basic stuff. We didn't even have television. We had the first transatlantic call after the first modern building in 1927. So that's what was going on in that time. Conditions were really bad worldwide. A lot of asthma, coal was being burned, right next to housing. So the International Congress of Modern Architecture formed in 1928. So the leading architects and planners of the times and designers got together, and this is what conditions were like. You couldn't even see that there was so much soot on walls, and they called for a whole bunch of things. That's how zoning get the housing out of the industrial areas, high-rise buildings with solar exposure and glass, so that you got light into them, and real utopian considerations. And Le Corbusier set out the principles for modern buildings: column wall separation, a horizontal glass, lots of glass, so you had good indoor-outdoor environment, lots of daylight, free design of the plan, and they even called for roof gardens. So that was the CIAM in 1928. By 32, we had an international style. Energy was so cheap, you can climate control any building. You can design modern buildings and put them anywhere in the world. We didn't have the first flight to even see the exhibit into New York till 1935. So that gets us to 39, and then Johnson built a single all glass house, showing you can overcome any environment with energy inputs. The beautiful Lever House, all glass building. Curtain wall construction then started in the early 50s and late 40s, and you began to hang single glass walls off of frames, get them high-rise buildings, and then you had the first modern town. We did all that in 27 years, and we did it with primitive design tools. Think about what we have now. The first ink pen didn't come in until 1960. We used to have to draw with an ink and then scrape the ink off if we made a mistake off the drawing. We got the first ink pen in 1960, and then the first laptop came in 1991. So the world was transformed in just 27 years with primitive tools. And think about what we have now and the computing power and the laptops. And I'm talking to you through Zoom. And we have hundreds of people listening to this presentation. Think about, it used to take us a year, 2 years to do a set of working drawings. Now we do them in a month, 2 months. So can we meet the 1.5 degrees C carbon budget? Everything is in place to do this. Of course we can. It really is up to our community, the design, planning, construction, and materials production community. It's those who are responsible for the built environment. We are the gatekeepers and we can do this. Thank you so much.